All right, it's 3 p.m. Hello and welcome everybody to this session on virtual reality. My name is Aske Mottelson. I'm from the University of Copenhagen, and we have 3 very interesting papers today in this session. The first one is about VR for AR prototyping. The next one is about gaze selection in VR, and the last one is about particle physics data visualizations in AR. And please bear with me for any technical issues. This seems to be rather difficult, but really great when it does work. And for everyone who wants to contribute with a question, please just write it in the chat, and I'll ping you. And then if you can please turn on your video for actually asking the question, that'd be great. Otherwise, I'll try to read it aloud instead. But without further ado, let's go to the first talk by Elisa Burova from Tampere University. The paper is called Utilizing VR and Gaze Tracking to Develop AR Solutions for Industrial Maintenance. All right.
Hello everyone, my name is Elisa Burova and I'm virtually here to present our paper, which was written in collaboration with industry, with the Kone Corporation, and called Utilizing Virtual Reality and Gaze Tracking to Develop Augmented Reality Solutions for Industrial Maintenance. The goal of the paper was to explore the potential of virtual reality technology coupled with gaze tracking to address prototyping of industrial AR solutions. We focus on how experts involved in the development process perceive the benefits and challenges of the approach in the industrial. Augmented reality is known as a promising technology for industrial maintenance, and in particular, it's been applied to provide in-field guidance and enhance safety awareness. However, the development of augmented reality solutions is often frozen in the proof of concept state due to risk associated with testing in hazardous industrial context. Industrial training in VR brings significant value due to the extended adaptability and the possibility to safely simulate dangerous operations and contexts. Moreover, the flexibility of virtual reality simulations make them a feasible and efficient approach to address augmented reality development issues. Within VR, potential AR concepts can be evaluated in a realistic, simulated context. An aspect like information presentation, interaction techniques, and context-sensitive functionality can be tested in a safe environment. Integrated to head-mounted display gaze tracking provides extended analysis possibilities for the usage of the augmented content and other user behavior, and it has been already applied to measure learning and safety awareness. In VR prototyping and training, gaze tracking can provide an understanding on how maintenance technicians perform their task, how they notice and utilize the elements of AR. To address our study goal, we developed the XR Safety Kit Framework, a multi-purpose virtual reality platform with augmented reality simulation and gaze tracking to support both augmented reality prototyping and virtual reality trainings. The system was made with the Unity game engine and the existing 3D CAD models of an elevator shaft, technical elevator components, and maintenance tools. The distinctive feature of our VR-based system is the augmented reality mode, where augmented reality field of view is simulated by displaying content over a rectangular area, 40 degrees horizontally and 27 and 5 degrees vertically, which is centered to the user's field of view. This mode allows evaluating of IR features, in our case in-field guidance and safety awareness, in a safe and controlled environment. It also allows the testing of different hardware aspects of augmented reality presentation, such as field of view, image quality, colors, and transparency of objects, and so on. The system allows training of remove and replace tension weight maintenance task. To provide step-by-step guidance, we created a documentation panel tool. We call it Doc Panel. It visualizes instruction in the form of text, pictures, and animations over a wide square. The user can move the dock panel in the 3D space freely and center it to eye position. The instructions are extracted from existing technical documentation in HTML format. We also designed 3 multimodal warning types to inform the user about possible hazards. The first one, the animated safety warning, uses an animated picture to explain the danger and appears over a risky area when the user interferes with it. When image is out of the user's field of view, the system visualizes a red arrow to point at the danger and makes a warning sound. Second is textual notification, which uses text and image to explain the risk. The notification is displayed over a risky object and stays for the duration for maintenance subtask. Third type uses image to notify about the danger and voice to explain it. Red arrow also appears if the image is out of the user's field of view. There is a brief demo video to visualize what is documentation panel and other system functionality. This is a feedback sound. The system assists the user by highlighting all the components related to the task. And there is animated safety warning. The described system design is a result of iterative user study with experts. The first iteration was carried out to verify the concept and collect ideas and requirements for the system. 4 expert participants explored the designed virtual environment without defined instructions and answered interview questions, which determined our design solutions. The second iteration was focused on investigating the usability and efficiency of the in-field AR guidance and warnings in general. The outcomes of this stage resulted in the deployment of 3 types of safety warnings and advanced logging for gaze data and virtual objects. The focus of third iteration was purely on safety and evaluation of document panel usage with gaze data. The second and third iterations were based on performing the maintenance task in the system, and in total 9 male experts participated. 2 of them had no experience in elevator maintenance, but were specialized in information architecture related to it. The rest has at least 25 years of elevator maintenance experience, with a mean in 15. The evaluation session took place in a spacious meeting room in the premises of the company. Prior to the virtual maintenance task, the participant had a training session to get used to the environment and learn system functionality. And after completing the task, the participant filled in the questionnaire about their experience and answered the interview questions. The majority of the participants show enthusiasm toward the idea of utilizing a head-mounted AR display for in-field assistance. The main advantage was seen in easier access to information and safety awareness. With provided guidance, all the participants in both iterations successfully finished the maintenance task. The documentation tool was found to be useful for the maintenance context. The participants spent on average 35 and 4% of the session reading the instruction. Gaze data showed that participants were able to read the instructions from documentation panel without directly facing it. On average, the gaze vector angle suitable for reading was over 7 degrees. All the participants verified the need for visualizing in-field safety warnings in a real context. However, not all safety warnings were observed by the participant. The analysis of gaze data from third iteration showed that the participant's gaze was directed on animated safety warnings. Only 4 out of 20 times the warning was displayed, clearly demonstrating the failure in design. However, textual notification was found to be the most successful and was noticed 7 out of 8 times it was shown. The XR Safety Kit framework was perceived as a viable innovation for the industrial context. The participants showed eagerness about the possibilities of working with both AR and VR technologies in their daily routines, and further ideated on how such technologies could be integrated into the company's processes for testing new maintenance method and technical documentation and for risk assessing. After the iterative study, we utilized digital content from the system and created a digital survey with the goal to gather expert opinions on the usefulness of the AR within VR approach and gaze tracking in the context of industrial maintenance. The digital survey consisted of 3 parts and included textual description with videos, open-ended questions, and 29 statements answered on a 5-point Likert scale. 12 experts, 10 male and 2 female, participated in the survey. The survey results showed a positive perception of and eagerness in utilizing AR, VR, and gaze tracking technologies. The AR within VR was found to be efficient and safe approach for industrial AR prototyping, while head-mounted display integrated gaze tracking was seen as a viable analytical tool for prototyping, training, and documentation development. The XR safety kit framework was found to be suitable in the industrial context due to flexibility, safety, and advanced analytics. It provides a safe and resource-efficient way for AR prototyping, which may be easily deployed by utilizing existing materials in industrial context. Integrated gaze tracking brings an advantage to gathering detailed and objective data for further analysis, which could not be gathered via traditional user study methods such as interviews or questionnaires. Finally, our work shows the potential of the whole mixed reality continuum to address other industrial processes and enable collaboration between different departments. This may be further explored to support virtual collaboration, training, and documentation and method development. Thank you very much for your attention.
Okay, thanks to Alisa for this presentation. Now is the time for questions. So if you have any questions, you can just share them in the chat below. You can either write to everyone or to me personally, and I'll make sure that you get a chance to ask a question. But let me just start off while you write down your questions. So this talk or this concept of using virtual reality as a medium for AI prototyping, Alisa, could you elaborate on as augmented reality technology matures, for instance, that you can bring down compile time or that it's easier to deploy as a headset? I mean, if you think that the technical difficulties in actually producing content would be as easy for AR as it is for VR, what do you think this prototyping for AR in VR would look like? Or is there a need for it in such a scenario?
Well, I definitely see that there is a need for virtual prototyping for industrial context, because even though the technology is working 100% sure, it's not like this. Like, you need to be sure that technology is working and will be capable to show the warnings, like show the risk associated, or even the technology itself can cover some risky areas in the industrial context, which will cause more damage. So I think that before going in the field with any as good technology as possible, you need to test it in a simulated environment. And this is a big concern in the industry as well. Does this answer your question?
Yeah, good point. So because you can't simulate things as well in AR, you would want to develop in VR as a precursor to doing it in AR. So we have a question from Juni Kwon. Maybe you could turn on your video and ask the question yourself. We don't really get any sound from you, Juni. Okay.
Sorry. Finally, I can reach out, right? So
that's good.
Can you
yes,
hear me?
Go ahead.
Yes,
we can.
The age group of the participants are a bit mature from my observation. Do you have any specific reason for the recruitment, or just it happened?
And the specific requirement we want to keep is waste knowledge in the industry. Overall, were pretty knowledgeable. So as I mentioned, only 2 had no prior experience of maintenance as it is, but they've been working in the information design structures, but the rest had experience in the field and further continued working in the company on other roles like maintenance method developers or safety method developers. And the goal was to firstly find their opinions and get their experience, insight from their experience to make the system better according to human-centered design development. But we have plans to observe the difference between novice users and trained maintenance technicians. And we are planning a study to utilize GAZE to see, I mean, like, it is well-known fact that GAZE is being utilized for evaluating the level of expertise. So that's what we also want to work with. But
so it's a byproduct of expertise.
Well, yeah. So instead,
okay, thank you.
Fresh, yeah, thank you.
Just to follow up on the expertise. So in the paper, you describe how some of the participants are experts in mixed reality. Some of them are experts in elevator maintenance. Can you elaborate on the differences in how they enjoyed the system based on their expertise?
Firstly, what I would like to say that during second iteration, the reaction to the system was the perception of the system was lower and the trust was lower because there was few bugs and issues. But after we fix it, we have 4 participants, and the participants who had more experience with VR, they felt more confident in the environment, while the participants who used it seldom or never used it, it took some time for them to get used to it. But that's the only kind of observation in the perception. Most of them would love to have these technologies, but some show a mistrust to the current state of technology. So once we would be able to show them that it's completely free, completely safe, and you can freely use it in a dangerous context, all of them would be happy to have this kind of assistance comparing to the paper documentation they have at the moment. Not only paper, they also have online tablet-based documentation, but still everybody's looking forward to working with something more interesting. And as for other things, we also noticed that these experts, they eager to try transiting their working tasks into virtual environment. And there is a lot of common tasks different departments do. So creating virtual environment to support their collaboration is basically the finding of the paper and the goal for our future studies.
So there's another question from Christopher Clarke. If you could just turn on your video and ask the question.
Hello. So I just really great talk. I was just wondering if, for example, because this is about safety warnings in VR, so is there any kind of showing the ramifications of doing something wrong or ignoring those safety warnings? Could you kind of show the consequences of those in VR?
Well, I would say for now, we have not been designing for this from this perspective. This study was to see if it's feasible to test augmented reality content in this environment and how GAZE data can provide us more information. But I'd say that the study didn't go to the direction you mentioned. Of course, we had our discussions with the industrial partners. What are the dangers of ignoring these things? But there is no, I cannot give you a very clear answer to this question because we have not been studying it in details.
Fair enough. Could you elaborate on how the results of your study could help other areas other than industrial maintenance, or if that's even something that it touches upon?
I suppose that if there's companies who are following the trend of digitalization and they have their working materials in a digital 3D forms, for example, there are some manufacturing companies, they can try to use our framework for their own prototyping. Of course, I understand that the scenarios and the environments would differ dramatically, but there is still some common findings. And in addition, we also provide a few tips on how to design those safety warnings for the dangerous contexts. So that can be a start for more deeper research in the topic.
Interesting. And maybe just as a last question, so the sessions that you ran were around 15 minutes, if I'm not mistaken. Could you elaborate on what do you think prolonged usage would have an effect on your findings, if any?
Well, I would say firstly, I would like to clarify that the maintenance task performance take on average 13 minutes, but the session took on average about 40 minutes because there was a lot of introduction, training process. And yeah, can you please repeat the second part of your question?
No, I would just be interested in if you used your system for longer times, how it would have an effect on your findings. If any.
Yes, thank you very much. I would say that head-mounted displays are still not comfortable for a longer use. And some participants said that, yes, it was maybe a bit heavy or a bit clumsy. But, and we did not run testing to check if the users are capable to work in head-mounted displays for a longer period of time, but we are definitely willing to do so in the nearest future.
That's completely fine. Thanks a lot for the talk to Alisa. If we could just give a round of virtual applause. That was a great talk.
Thank you very much. Have a nice conference.
All right, let's move on to the next talk. The next talk is going to be presented by Ludwig Sidenmark from Lancaster University, and it's called Outline Pursuits, Gaze-Assisted Selection of Occluded Objects in Virtual Reality.
All right, thank you. I'll just turn on the video. Hi everyone, I'm Ludwig Sidenmark from Lancaster University, and with me for this presentation we also have Clarke from Lancaster and Xuesong Zhang from Leuven. And we're going to present our work on outline pursuits, gaze-assisted selection of occluded objects in virtual reality. Occlusion presents a principal problem for selection in 3D environments. This reduces the target area for pointing and increases selection ambiguity. Users can change the precision to improve the view they have of an intended target. However, this is a limited option when movement is restricted, such as when sitting, or if the tracking space is limited. In this work, we propose to support selection of occluded objects with outline pursuits. As shown in the figure, the concept is to display the outlines of objects that lie in the pointing direction and to generate a distinct motion along each outline. Users can then disambiguate the selection by following the motion around their intended target with their eyes. But before we go into the details of outline pursuits, I would like to take a step back and look at some related work. Raycasting is commonly used for selection where the user controls a ray via a controller or body part. However, targets at greater distances are harder to select due to limitations of human motor control and motion tracking. To compensate for accuracy and occlusion issues, raycasting can be combined with volumetric techniques for selection, which require disambiguation from initially selected objects. And this can be done via a manual step or by applying heuristics or contextual information. With gaze, it is easy to be accurate from a user perspective, but sensing is difficult, which limits usability. Pursuits offer an alternative selection technique where the user follow a moving target with their gaze. A selection is then performed by correlating the target and the eye's motion trajectories without the need for eye tracking calibration. Selection is robust, provided candidate motions are sufficiently different. Prior work has used smooth pursuit for selection and disambiguation in VR, however, for selection of objects presented in motion. A distinct novelty of our work is that we instead present motion around static 3D objects to facilitate their selection by pursuit without changing the object's size or position. With that being said, Chris is now going to break down outline pursuits and the steps of interaction.
Thanks, Ludwig. From a user's perspective, selecting an object using outline pursuits involves two stages. The first stage is candidate selection, which is used to reveal potential targets using coarse-grained pointing. The second stage is selecting one target from the candidates using smooth pursuit-based selection. We will first look at the candidate selection stage, which consists of cone casting, outline extraction, and motion generation. Candidate targets are selected using a cone casting technique. This stage is designed to encourage coarse-grained, lazy pointing, which can be performed with any type of pointing modality and reduces visual clutter. As we are in a controlled virtual environment, we can accurately extract the outline of virtual objects to reveal objects available for selection and to provide a predictable path for smooth pursuits without having to change the properties of the object itself. Once we have extracted the outlines, we can augment them with target movements to be used for smooth pursuit selection. The goal here is that each moving target moves in a unique trajectory. In the first instance, we utilize the direction in which the targets move to create two groups, clockwise and anti-clockwise. For more than two candidate targets, we set the number of rotations per second to be equal. We then maximize the phase differences between target movements to ensure each trajectory is unique as possible. We also have to carefully consider how to present outlines and target movements in the presence of occlusion. For this, we looked at 4 different variants. Whole outline, where the entire outline is visible, even under occlusion. Shared outline, where the target moves along the visible part of the object. Cut outline, where the target moves along the shortest path to the next visible part. And jump outline, where the target jumps to the next visible part. A user study with 16 participants revealed that performance and usability ratings were consistent across the outlines. This indicates that designers can freely choose an outline that fits their application without risking major performance penalties. Once the candidate targets have been revealed, the final stage is to select one of the targets. This is achieved using smooth pursuit eye movements to disambiguate one target amongst many, followed by confirming the selection. Target disambiguation occurs when the user follows the relevant target using their gaze, resulting in smooth pursuit eye movements. The system takes as input the user's eye positions and all of the candidate target positions as spatiotemporal trajectories. We then calculate a similarity metric for each target to determine which, if any, the user is following. Traditionally, disambiguation and confirmation occur in a seamless fashion for smooth pursuit interactions, when the similarity value of one of the targets surpasses a threshold. In this work, we also consider separating disambiguation and confirmation stages, which removes the need for a threshold. This may be used for selection based upon specific timing, or when a user wishes to highlight or learn more about an object prior to making a selection. I will now hand over to Xuesong, who will discuss the techniques and applications we built based on outline pursuit.
Thanks, Chris. We demonstrate outline pursuit with the implementation of 2 concrete techniques, one for hands-free selection and one extends controller-based recasting. Each leverages a different coarse-grained and selection confirmation mechanism. The hands-free version uses the head field candidate selection and the similarity threshold for confirmation. This technique allows for hands-free applications or for users to interact with out-of-reach objects without having to put down or stop interacting with virtual objects already in hand. We developed a virtual cityscape application to illustrate this technique. The application lets users explore the city and buildings using only their head and eyes, with selection triggering additional information. In contrast to other gaze-based techniques such as gaze duel, hands-free outline pursuit enables a user to gaze upon objects for an indefinite period without making a selection. The second technique is controller-based outline pursuit, which utilizes controller-based pointing in the coarse-grained stage and a button click to confirm the selection. We developed a room planner application to showcase the technique. users can select and manipulate objects that are occluded or in close proximity to each other without forcing the user to change their point of view or hand position. This means users are able to select an object with little hand movement and thus plan their hand placement for the following object manipulation. Separating disaggregation and the conformation stages allows the user to check additional details prior to conforming selection. We designed and conducted a user study to investigate the performance of the proposed outline pursuit techniques against the baseline techniques and gathered user feedback. In a VR environment, participants were tasked with selecting a target object among many as fast as possible. We varied the object densities, distance to the user, and the levels of occlusion. We measure selection time, error rate, head and controller movement, and the user's preferences. Hands-free outline pursuits required minimal head movement and showed no difference with the baseline technique at high occlusion. However, it suffered from higher selection times and error rates, despite feedback stating the interaction technique was simple. This was in part due to some participants not reaching the required threshold for selection, which resulted in large variance across participants. Controller-based outline pursuits achieved consistently low error rates across all conditions. It also required less movement from the participant, independent of the level of occlusion or distance to the target. Preference-wise, users feel there was little difference between conventional recasting and outline pursuit techniques. However, many favored recasting because of the faster selection time at low occlusion. Now back to Ludwig for the conclusion.
So to wrap up our talk, we presented outline pursuits, which is a novel technique for effective selection of occluded objects in virtual reality. Outline pursuits does not require line of sight and requires minimal body movements for selection, making it ideal in situations with restricted movements. By adding to the already existing utility of outlines, objects can be selected without changing their properties. We demonstrate how combining smooth pursuit for disambiguation with other modalities for confirmation reduces the parameter search space and risk of accidental activations, while providing more opportunities for the provision of feedback. Our results show the compelling advantages of outline pursuits for highly occluded targets, which opens up further possibilities of combining the techniques with alternative selection techniques to allow efficient selection at all levels of occlusion. And that was all we had for this presentation. Thank you for listening, and we're happy to take any questions.
All right. I can't hear you, it's muted.
Oh, okay, I forgot to unmute myself. I just said thanks to Ludwig, Christopher, and Xuesong for the presentation. Now's the time for questions. So if you have any, just drop it in the chat, and I will select you for questioning. The first question is from Jens. Please turn on your video.
Hi, Ludwig and colleagues. Yeah, as Ludwig knows, I'm familiar with this work. I think it's a really cool technique. But I just had a question. So have you actually experimented with scalability of this technique? When are these outline patterns sufficiently, you mentioned sufficiently different in the beginning.
Yeah.
What does that mean? And how much clutter does it actually scale up to?
So you mean scalability as in how many outlines to
Yes.
show at the same time?
Exactly.
Well, the reason why I think it can become a potential issue, especially when the outlines are so like visually attention grabbing as they were in our examples. One thing we didn't look into that much was, how to make it more subtle and things like that. And then I think you could present more motions. In general, we didn't play around with that much. We picked 4 because we thought that was a good trade-off between having not too much fine-grained pointing when you do the initial pointing, but still limiting the visual clutter. I mean, at the same time, you don't want outlines to be presented anywhere all the time. As you say, it can become very annoying for the user. And I think that would be the main kind of bottleneck. You know, there's been plenty of work that has shown that you can present a lot of different motions, but it wasn't really anything we looked into that much.
Just to follow up a bit on that question, could you elaborate on the design decisions? So why did you pick these particular movement paths, and like a sort of design theory that goes behind the choice of these?
The four different movement paths you mean during occlusion. So we picked them based on, basically tried out a bunch of different ones, and these were the ones we thought made sense. We couldn't really come up with any other ones, so these were the ones we tested. And I think really it comes down to what we did in the paper was we stick to the one that always shown the full outline. And the reason why we did that was because, well, it was the only one that you can show when the object is fully occluded. Because the other ones, well, they kind of adapt to when part of it's occluded, but when the whole thing is occluded, it doesn't follow that same kind of style anymore. So it's only the whole occluded one that works then. When it comes to the appearance of the outlines, our goal was to basically make them to stand out, and so that it makes it easier for the participant or for the user to basically follow the motion. But we didn't look that much again into the visual parts of the outlines.
Yeah, fair enough. So I was wondering, in most settings you don't have occlusion. It's kind of a special
Sure.
issue in selection. What about situations where it's obvious which object would be your preferred selection? Would you still have to follow the path, and if so, what kind of delay would you expect on a regular interaction basis?
So for the controller one, when you do the pointing and there's only one target in the direction, it picks that one automatically. So then you don't have to follow the motion. Otherwise, yes, you still have to go through the whole thing of going through the motion and so on. This is what we found in the user study, where they liked it, but it felt a bit unnecessary when there was no occlusion. And this is kind of where I think all of these techniques that kind of have to deal with occlusion, they almost always involve these extra steps. And these extra steps are usually unnecessary when this selection is simple. So I think in the future, it would be interesting to look into techniques that kind of can detect, okay, now the user is having trouble selecting something. Let's go into this occlusion selection mode and try to select it and use that technique instead. So it can kind of allow efficient selection at all levels of occlusion.
Sure. So occlusion is not a particular virtual reality issue. I'm sure most of you are familiar with occlusion on just a regular desktop interface. Say you have multiple icons on top of each other and you want to pick one of them, or you have multiple windows that you have to scale or minimize. Do you think this technique could work for other mediums than virtual reality? And
so,
what kind of limitations are there?
So the reason why we did in virtual reality is because, well, basically all the information about the objects, about their shapes and so on, is present, and we can extract that. If you would do the same thing in augmented reality, you would probably need to either have some very advanced computer vision algorithm that's probably very computationally heavy, or you would somehow need to extract the shape of the object somehow. So I think that's the main limitation when it comes to AR. When it comes to desktop, I see why not, why you can't use it, but then you have a mouse and maybe you don't want to use your eyes. I don't know.
Sure, but the mouse can be an issue as well.
That's true.
In occlusion selection. So another question. So have you had any considerations regarding the cognitive load of this method? So obviously it requires you to think a bit more than just clicking an icon or selecting from a list. It does require you to follow and then focus on that point. Do you have any estimate of how cognitive demanding this is for the user?
So when we did the user studies, no one really complained that much that it was very straining to do or anything like that. But I do know that, you know, some people are better at doing pursuits than other, and I think it's part of a training thing. And it's kind of interesting because when you do these pursuits, I usually tell people that, you know, don't think about it, just follow the motion, and usually it just works better for them, because the more they think about it, the more they start to try and predicting the path, and they move their eyes in different ways and so on. So I think it's just you have to get used to it, and it becomes much easier for them to do. But I think when it comes to cognitive load as well, it kind of is tied in with the whole clutter part, where, you know, you don't want to show too much and try to like overwhelm the user or anything like that. But again, we didn't try around that much to see where the limits are and so on. But in general, we didn't find that it was too straining.
Fair enough. So thanks a lot to Ludwig for this talk.
Thank you.
That was really interesting. Let's have a round of virtual applause for the presenter. All right, we have another talk coming up. It's by Xiyao Wang. It's called Towards an Understanding of Augmented Reality Extensions for Existing 3D Data Analysis Tools. And Xiyao is from Sidenmark.
Share my screen. Yeah. Thank you. Hello everyone, my name is Xiyao Wang. It is a great honor for me to share our work towards an understanding of augmented reality extensions for existing 3D data analysis tools, and one of our co-authors is from Nordic countries. The background of this study is that it has been largely studied by many researchers that immersive visualization with stereoscopic views help understand 3D datasets, and many of them have been created during the past years, ranging from large ones like a cave system to smaller ones like head-mounted virtual reality or 3D glasses. Even though the benefits of visual immersion have been demonstrated by many studies, for example, controlled experiments have proven that users can understand biological structures easier with immersive environments than a normal screen. Few of them have been practically integrated into scientific workflow. We thus want to investigate a practical way to bring immersive visualization to their daily workflow. For this project, we are working with domain experts in particle physics. This is an example of particle collisions, and in general, one event is very large. As we can observe here, it is hard to understand how particles travel in space, and so they have interest in using immersive environments to explore their data. However, they do not only rely on visualization to understand the data. A common approach is that they first use some statistical tools to analyze the data, to find the regions of interest, and then, with visualization software, they try to understand the events. Very often, they need to consistently switch between the analysis software and visualization tools to accomplish data exploration tasks. There are some important elements in this process. The first is that traditional analysis tools heavily rely on script typing and precise parameter adjustment, where mouse and keyboard are still demanded. Secondly, 2D plots like histograms and normal table numbers are still very important for experts to observe some phenomena. Thirdly, they need an efficient 3D visualization tool. Based on these considerations, we investigate an AR extension to existing data analysis tools. In this project, we use the Microsoft HoloLens. The general design comes from the scenario where experts use two screens, Users use a mouse to interact with both screens. The cursor can go from one to another. Then, one screen is turned to the HoloLens. In this study, we keep the same interaction on the PC and on the HoloLens. We still use a mouse to control both spaces. The cursor can go from one to another. We detailed our design choices and make difference from previous ones in our paper. We encourage you to read it if you are interested. We implemented similar user interfaces on both sides. The left side is on the PC and the right side is on the HoloLens. Users can perform the same functions with any part. Based on our discussions with physicists, we implemented some basic functions to explore their datasets. We only show a very short concept here. As mentioned, both sides have similar interfaces, and any functions can be performed on either side, on the PC or on the HoloLens. And here is another example is that we can draw something and filtering it with a lasso tool in AR or on the PC. Then, to understand how experts would want to use such a linked view design, and also to gather any other possible comments for future design, we performed an observational study with 7 physicists from CERN. This study is pre-registered to follow the open science practice. The experiment is composed of 3 main parts. First is a tutorial and explanation, where the experimenters introduce the system and the supported functions, and then a free exploration phase. We asked participants to freely explore a simulated dataset with all possible functions. During this process, the experimenter stays with the participants, take notes, and help them if needed. We also encourage them to ask questions and think aloud. At last, we conduct a semi-guided interview to get their comments. We briefly summarize some of the main insights for our study. For more complete results and discussions, we highly encourage you to read our paper or to contact us directly. First, the hybrid setting is feasible and useful. Both sides have their advantages and can benefit the data exploration process. For example, on the PC, with the PC using mouse and keyboards, the experts can still continue working with their used tools, and also it is reported that they are all trained to understand things on the PC and use the mouse. And with the HoloLens, they can better understand the event. For example, with the depth clue, participants could understand better how particles are traveling in space. They can easily follow Wang trajectories, and also it is easy to understand the spatial arrangements in space, both between the particles and between the detector chambers, which are also important to understand something. Then, the AR canvas with unlimited space facilitate the view comparison. As in many other scientific domains, the scientists rely on multiple views to understand the same datasets, and the AR spaces with unlimited space can help them to put many things at the same time and to look at them differently. It would thus be a good idea to be able to add, move, and adjust the content in AR spaces. However, the mouse in AR with some technical issues still needs further investigation, like much discussed in previous desktop VR settings. Also, working around data in AR is seen as a great difference from a screen and from the VR system. where the users are tied to a PC. One participant particularly mentioned that he noticed the advantages of stereoscopy once he stands up and walking around. And also, there are also many other comments reported by the participants, such as synchronization between the two spaces. In summary, the hybrid setting is a feasible and useful way to bring immersive visualization to the scientist data exploration process, and it's worth to be further investigated. For example, the large AR canvas and walking around have great potentials, but the interaction maybe needs to be further investigated. So in the future, there are mainly two directions we are working on. The first is how to support both intuitive and precise interaction, especially if we want to support the interaction while the users are walking around. And also, we want to test our settings with more realistic tasks, such as a TrackML challenge. If you are interested, feel free to contact us. I finished my presentation, and thank you for your attention. And I'm ready to answer any of your questions.
Okay, thanks to Xiyao Wang for this presentation. We're ready to have some questions for this presentation. You can just drop them in the chat below, either to everyone or just to me personally, and I'll pick someone to talk. But in the meantime, I can just begin.
Okay.
So it looks super cool with this multi data visualizations, both on screen and in AR. Can you maybe elaborate on how large of a canvas outside of the screen is meaningful? I mean, to what, when does it get cluttered, and when does your attention span reduces too much because of too many data visualizations?
Yeah, fine. In this project, there are not much like the occlusion problems or so much, because we define the views in space in a clear way that they don't occlude with each other. So from the result of our experiments, the only thing that the large canvas is an advantage because they can range things around the users everywhere and provide things to make it bigger. So with our design, we don't think that or from the experiment, we don't find anyone reporting there will be some problems when the canvas is too large or has too many content on it. I'm not sure if this answers your question. So.
No, that's fair. It was also only if you had some sort of observation that when you add too large of a canvas, it might increase too much.
Yeah, I understand. Load. But from our experiment and with our design, we didn't find such comments because views in space, we define it in some constrained way that they don't load each other or have some other terrible effect, I think.
Yeah. So in the paper, you write that some users, they describe field of view as a technical issue that limits the usability of this system. Could you elaborate on how does this limit their use of the system, and what other technical difficulties did arise during your evaluation?
Yeah, the thing is the data set usually is very large. For example, the data set we are using for the experiments contains more than 10,000 particles, and each of them have a trajectories in space. And very commonly, they want to zoom the views to look at the particles in a more detailed way. So in this case, it would be better if they have a larger field of view. For the current state of the HoloLens, the view is still very limited. They need to move their head very often to follow one particle instead of observing the whole traveling trajectories. So this is one of the problems they raise for the limited field of view of HoloLens. And And also they like the large canvas of the HoloLens, but they still need to move their hand, to move their head to change their focus directions to see the different views. And it is also a disadvantage of it. But the main focus of these experiments, we are not asking them to look at the hardware. We are more like to encourage them to envision if the hardware can improve in the future, what potentials could it bring to us? Am I clear about that?
Yeah. So I understand that there's the field of view is just a current technical limitation in state-of-the-art augmented reality headsets. What I'm fishing for here is the trade-off between having an unlimited field of view and then overloading the user with data visualizations that might occlude the view rather than actually supporting the augmentation. So do you have a sense of what would be optimal in terms of field of view? So you mentioned that it would be nice if the field of view was bigger, but obviously that comes at a certain cost, I suppose.
Yeah, sure. But we don't really explore this point in our experiments. We just more like encourage them to think about in the future, if this is not a problem, how could we use such a system to help them explore the data set and how to help with the visualization with augmented reality. So I'm not very sure about this point. How do we do the trade-off between the different views?
Yeah, but that makes sense. So maybe just as a sort of last question, I mean, it's an interesting project, and I'm eager to hear what are the future plans of it, and what are some obvious things that you would like to implement in the next iteration.
Yeah, the first thing is maybe before implementing into the system, we want to first still compare some input devices. For example, the mouse have some issues in augmented reality. It also discussed heavily in the past research work, but we want to still understand, is it really a problem that could reduce the performance, or is it just some habit? For example, the users are not used to it, or something like that. We first want to do a study to understand how exactly the worse or good the mouse is compared to other inputs for our scenarios for the visualization. And also, when we want to apply it to a more realistic tasks, there are also many other functions needs to be implemented, because to analyze data, there are different perspectives to look at. For example, in our experiments, we only use histograms to look at the data with some parameters. But if we want to continue working on some further exploration of data set, we still need to implement some other analysis that are used by the physicists or some other domain experts.
Great. Thanks a lot for the talk to Xiyao Wang. Let's just have a round of virtual applause.
Thank you.
All right, that was our last talk. For those of you who haven't had enough virtual reality, I know there's at least a few other talks tomorrow about virtual reality. There'll be one at 11 in session 17, and also one at 9:45 in session 15. There might be others that I haven't seen myself, but thanks for watching this talk. I think it went better than I expected, like technically speaking, and also the talks were also great. Those met my expectations, definitely. So thanks to everyone.